So where are we at? We've talked about applications, and then we jumped into parametric curves. Now we're going to jump again. Now, parametric curves, the idea is we want to describe curves, and we're going to do it by this introduction of this parameter. We think of it as time, and we're going to say, well, where are we at a given time? And so we can think of this particle as moving, and we can say, where's the location at any particular time? Now, I will say you're going to revisit parametric curves when you take Calculus 3. And the big thing that's going to happen is you're going to be able to move not just in the plane, but in the third dimension. It's really good. It's like calculus in 3D. So what are we doing now? Well, we're going to jump one more time, and we're going to talk about coordinate systems. In some sense, we're very used to coordinate systems. And this was a very powerful idea. And it actually is not an ancient idea, at least not as ancient as many things in mathematics. A lot of things we trace back to the Greeks and their mathematics, and they loved lines and they loved circles. But they didn't have coordinate systems. So the idea of coordinate systems, it's only a few hundred years old, and that came about, a lot of people attribute to a philosopher / mathematician named Descartes. And legend has it that one day he was sick and laying in bed, and this was back before they had the Xbox, so he had to do something for entertainment. So he decided to pass his time by staring at a fly on the ceiling. And it occurred to him that, if he just described how many feet the fly is from one wall and combine that with how many feet the fly is from the other wall, that those two pieces of information would tell him exactly where that fly was. So that's sort of the idea of the Cartesian coordinate system that we're used to. So namely, if I have a point here, how do we describe that point? Well, we have directions, and we call these x and y. It's just convention. Nothing really sacred about those two symbols. And so we say, well, we go so many units over in the x direction, probably looks like 3 here, and we go so many units in the y direction, and looks like 4 there. And so we describe this by a pair of distances, 3, 4. So that's the Cartesian coordinate system. And once you had that additional sort of layer, so geometry, the idea of points and lines and circles, that goes back thousands of years. But once we added on this layer of let's bring numbers into geometry, that's when things really opened up. And we couldn't do calculus until we had this layer. Now, the goal for today is to talk about a different coordinate system. I want to emphasize, though, that we're not changing our geometry. So in other words, when we talk about the plane is still the plane. Points in it are still points. So we're not changing that. What we're going to change is how we describe where things are. So what we're going to talk about is something called polar coordinates. Now, how do polar coordinates work? Well, the basic philosophy is you want to describe where you're at in relationship to the center. So I have a center location. And now I have a point, let's say somewhere over here, and I have to decide how do I describe where that point is. And so here's the idea. What we'll do is we'll start off at our center location, and we have sort of a neutral direction. So we're going to call this direction 0. And then what we're going to do is we're going to rotate by some amount. We're going to call that an angle, theta, and then we're going to go out some distance, and that's going to become a distance we call r. So now we have our locations are described not as a combination of two distances, but as a direction and a distance. Now, this is not such an unusual way to describe things. And if you watch movies which are set, a lot of movies, for example, in World War II, which highlight what happened in the Pacific Theater, or anything that really, where you see big boats, they show this shot of this large revolving thing on the outside of the ship. Then they go on to the inside, and you see this dark room, and there's this screen, And then there's this line swinging around, and then occasionally it goes beep, and then it shows a little dot. And then, of course, it swings around again, beep, shows another little dot. That's called radar. Radar. And that's how radar works. Because the idea is, I want to say, where is everything in relationship to me? Which direction do I need to go? How far out is that thing? And what do I need to do? So these are not such unusual ideas. Now, what we want to be able to do is be comfortable. We're going to get a little bit more comfortable with polar. I mean, the thing is, you've had years of practice with Cartesian, so we're not going to get as comfortable, but we'll work on it. So, first thing is, we want to just talk about moving back and forth. How do we go from one coordinate system to another coordinate system? And the simple thing to do is, let's just put them on top of each other. Everything is the same underlying geometry, so I just need to figure out how do these two descriptions relate to one another. So here we go. Here's some point. And I can describe that point as a combination of x and y. So that's the Cartesian idea. And I can describe it as some combination of theta and r. And that's the polar idea. When we put all these pieces together, we see that we have something nice. In particular, we have a triangle. And of course, as you can probably tell, it's not just any triangle, it's the right kind of triangle. Has a right angle. So now we can start doing things. We have a lot of geometry facts. So let's just point some things out. We can use the Pythagorean Theorem. X squared plus y squared equals r squared. Nice. So now I can jump back and forth. If I know x and y, I can determine r. There's other things that are true. I can relate, because I have this angle theta in one corner, and I can think about, well, let's think about the trig functions. If I look at the cosine of theta, that's the adjacent over hypotenuse. Cosine theta is x over r. So that becomes x equals r cosine theta. Do the same thing for sine of theta. Sine theta is the opposite over the hypotenuse. So the opposite side is y, hypotenuse is r. So sine of theta is y over r, which tells us that y equals r sine theta. Now these three are the most important to know. And if you know those three, pretty much you'll be able to solve any problem that says transfer from one coordinate system to another coordinate system. Now the last thing to note is that if we use tangent, that's opposite over adjacent, so that tangent of theta is y over x. That doesn't get used quite as much, but it's a true fact. So, there is one thing to be aware of, and there's this comment here, that it is possible in possible in polar coordinates to describe one point in many ways. Now that's not true in Cartesian coordinates. If I have a pair, 3, 4, that's a unique point. And there's no other pair of numbers that describes that point. That's it. That's all there is. But in polar coordinates, we can do certain things. So for instance, if we were to spin around, so that is to say, if I were to take my space here, so here's the 0. If I go theta, I'm looking in this direction. Well, if I go theta plus 2 pi, I still look in that same direction. So there's this sort of like, well, if I look theta plus 2 pi, I'm in the same direction. Now, of course, the really fun thing, and some people disagree whether or not you should be allowed to do this, is if you go theta, but then you go pi, so that you're looking in the opposite direction. And now you're saying, aha, that's a different direction. But combine it with the fact that r, well, we never really said it has to be positive. We could have r be negative. And if r is negative, what does that mean? Well, it means that you turn in that direction and then you walk it back. So that's what r being negative means. So that you have all these strange possibilities that can emerge. So just be aware. Interesting things can happen. Okay, so here we go. Let's identify and sketch the following curves. So part A, theta equals 1/4 pi. What can we do? Okay, so someone says just draw the plane, all right. And then this says go up to theta equals 1/4 pi. Of course, they said 45 degrees, but we're in calculus, so we're going to say 1/4 pi. And now that's the angle for theta. Whoop, lost my mic. Now, how do we get all the points? What do we do? Yeah, it's all the points. How about these points? Yes. Yes. We're going to be flexible. We'll allow r to be negative. Now, is there another way you could do this? Well, you could, if you were being creative, which is not always bad, say, hey, I know something about tangent of theta, right? So let's just take the tangent of both sides. What is tangent of theta? Well, that's tangent of pi fourths. Tangent of pi fourths is also known as 1. All right. Well, what is tangent of theta equal to? Y over x. So we need that y over x equals 1 or y equals x. And there we go. Okay, so that's it. All right, so for part B, r equals 2 cosecant theta. All right, a little bit different, a little bit different. That's all right. We like things to be different. It's the spice of life. What can we do? Okay, so first thing is, you'll notice these do not have a cosecant in them, which means we don't want to be working with a cosecant. So we will, first thing is, rewrite it so there is no cosecant, 2 over sine. Now, what can we do with that? R equals 2 over sine theta. Okay, so someone has suggested, let's multiply sine theta to the other side. So r sine of theta equals 2. R sine theta is equal to y. So this becomes y equals 2. So that's not such a bad thing to draw. You draw a coordinate system and y equals 2. It's a nice flat line. So r equals 2 cosecant theta looks a lot like y equals 2. Now at this point you're probably thinking, isn't y equals 2 a much simpler description than r equals 2 cosecant theta? And the answer is yes, a lot simpler. And so now you're thinking, so why are we learning this? Well, just wait, we'll flip it around. There are some things which are very complicated to describe in Cartesian coordinates which are very simple to describe in polar coordinates. Right now we're just practicing. We're learning. We're young. All right. Well, last one. R equals, I should just stop standing near this drawer here. All right. R equals 3 over cosine theta plus 2 sine theta. What can we do? Yeah. Fractions, I've always struggled with fractions. And so I like to get rid of fractions as soon as I can. So, multiply it across. By the way, before we go very much further, any guesses what this is going to be by the end? Circle, maybe? Yeah, maybe. We'll find out. All right. Multiply it across. So r times cosine theta plus 2 sine theta equals 3. Well, probably should multiply the r through. R cosine theta plus 2r sine theta equals 3. All right. Now what? Okay, so we can use the fact that we know what r cosine theta is. We can use what r sine theta is. So we can say, well, this is x, this is y. So we get x plus 2y equals 3. Now can you see what it is? It's going to be a line. And probably if we solve for y, that'll be the simplest. So you get y equals minus 1/2 x plus 3/2. So I subtracted x and divided by 2. So what is that? Well, it's a line. It has an intercept at 3 over 2. I'll say that's 3 over 2. And a slope of negative a half. So there you go. All right. All right. Good. Well, don't worry. We're going to do a lot of these. We're going to get really good. Or at least we're going to do a lot of these. Here's another one. Okay. Identify and sketch the curve. R equals 6 cosine theta plus 8 sine theta. Okay. Well, the last one we had was a line. Maybe this one will be a line too. I know that you have a distrust of me, so you're probably thinking this is definitely not a line. It's probably a good thought. All right. What can we do here? We don't have any fractions, so fractions are not our problem. So what can we do? We could square both sides. Now, squaring both sides would be great for the left-hand side, because then we get an r squared. And we're like, yes, we love r squared. But it's not so good for the right-hand side, because then you get cosine squareds and sine squareds, and they're not the kind that like to hang out with each other. In fact, they don't like to hang out with each other at all in this case. And then you have like a cosine sine in the middle. So squaring, not a bad idea, but not going to help us too much. Is there a different way we could get an r squared, though, other than squaring? We can multiply by r. And we're allowed to do that. So let's multiply both sides by r. So if you did that, r squared, I'm just going to multiply it through 6r cosine theta plus 8r sine theta. All right. Now the good news is we have our r squared, which we like, but what's the other good news? We have r cosine and r sine. So your goal, if you're ever trying to convert something from polar into Cartesian, you want to get one of three things: either r squared, r cosine theta, or r sine theta, and some combination of those. So we are in our happy place. What does r squared become? X squared plus y squared. And that equals 6x and 8y. Okay, do we recognize what this is? It's a mystery still. Okay. We could go back to polar. When you see x squared and y squared, what do you think? Circle. So we're probably thinking circle. We should put the x's together. X's like to hang out with x's, and y's like to hang out with y's. Okay, so what can we do? Now, normally we'd like to think of circles as, something squared plus something squared equals r squared. The x squared minus 6x, it's not a square, though. We could complete the square. Whew. Thank goodness, I seem to have left some space. That's going to be very useful. If I complete the square, what do I need to add to this x squared minus 6x? Plus what? 9 is correct. Because you divide the middle term by 2, and then you square it. And if you did that, that becomes x minus 3 squared. What do I need to add to the y squared minus 8y? 16. Take the middle term, negative 8, divide that by 2, gives you negative 4, and square it. That makes this term y minus 4 squared. Now, if you add 9 and 16 to that side, you need to add 9 and 16 to the other side. If I add 9 and 16, that's 25, which we can think of as 5 squared. So we have x minus 3 squared, not equals, x minus 3 squared plus y minus 4 squared equals 5 squared. So now, do we feel comfortable with what this is? It is a circle. Where's the center? 3 and 4. Positive 3, positive 4. Because remember, it's x minus the x coordinate for the center, y minus the y coordinate for the center. Okay, and so if you draw this, we can come up here to 3, 4. And if you think about how far 3, 4 is from the center, it turns out that the distance to the origin is 5, which means it passes through the origin. So what we end up with is a circle. Well, you have to imagine that's a circle. But it's a circle which happens to just pass right through the origin. That's it. So we'll mark the center, 3, 4. All right. R squared equals secant of 2 theta. Now, one thing that I really don't like is the fact that I have a 2 here. Because all my identities that we've talked about, that x equals r cosine theta, y equals r sine theta, it's just something of theta, not 2 theta. So we want to get rid of the 2. So how can we get rid of the 2? Well, we've got to think about that. Well, we want to, something like double angle, but do we have a double angle formula for secant? Oh, somebody has said, secant. We wouldn't want to work with secant. Secant is 1 over cosine, which is a true story. Let's get rid of that fraction before we deal with the 2. So multiply both sides through. We're going to get r squared times cosine of 2 theta equals 1. Now, what can we do with that 2 theta now? What do we have available to us? It's like I have an angle that's been doubled. I have a doubled angle, and I'm hoping there's an identity. Yeah, somebody mentioned double angle identity. Okay, now's our chance to shine, because we sat down and memorized all our identities for trig, right? So, double angle formula for cosine becomes, cosine squared minus sine squared. Good. I'm glad that we memorized that, because it's one of the 6 identities that we need to know to get us all the way through calculus. Okay. So, now what? Well, what can we do? We can distribute the r squared through. Another way to think of r squared cosine squared is r cosine theta squared. Another way to think of r squared sine squared is r sine theta squared. So what does this become? X squared minus y squared equals 1. All right, good. Now, x squared minus y squared equals 1. What does that look like? It's not quite a circle. It would be, if it was x squared plus y squared, it would be very circle-like, circulaceous if you would. But it's x squared minus y squared. We have done this before. We've done this within the last week. It's not an ellipse. It's a hyperbola. And people are just like, what is this fascination with hyperbolas? Okay, now let's test if you remember. Asymptotically approaches the lines y equals x and y equals negative x. Now, is it going to open off to the sides or up down? One person has suggested up and down. Any votes for to the sides? Because it's to the sides. Now, you're probably thinking, how would you know that? Well, because you paid attention in your algebra class when you were in high school. And like, I love algebra. Hyperbolas are cool. And the other way is to think about it is, where does it hit the axes? When in doubt, just ask yourself, what happens with the axes? Does it hit the x-axis? Well, x-axis is y equals 0, and it does. It hits it at plus minus 1. Does it hit the y-axis? No, you can't hit the y-axis because that would be negative something squared equals 1. Can't happen. All right. In case I've made you nervous about you having to memorize hyperbolas, we're not going to make you memorize hyperbolas. These are just fun examples. Oh, whoop. Oh, don't want to reveal too much. Okay, sketch and indicate the region where r goes between 1 and 2, theta goes between 0 and pi halves. Okay. So, r goes between 1 and 2, and theta goes from 0 to pi halves. So we got to sketch it and indicate with this shade. So first off, let's start with r going between 1 and 2. What does r equal 1 look like? So circle of radius 1. So someone said it's distance 1. That's a good way to think about it. So r is how far you are from the center. So if I look at r equals a number, regardless of what that number is, it's a circle of that number centered at the origin. So r equals 1 is a circle of radius 1. How about r equals 2? Circle of radius 2. So, probably should have drawn a better picture here. But, so r equals 1. We have a circle of radius 1. Imagine that was a circle of radius 1. And r equals 2. Well, that's a circle of radius 2. Okay. Now, theta between 0 and pi halves. Well, which way does theta look? Which axis am I looking down if I say theta equals 0? Positive x-axis. So that's theta equals 0. It's that way. Now, where is pi halves? Positive y-axis. I've rotated an angle of pi halves. So I want to have theta go in between. So I'm looking in the first quadrant when I say theta goes between 0 and pi halves. So what's our region? Well, we've got to be inside the first quadrant. That's what our range for theta says. And then our range for r says in between these two circles. So that tells us that this is our region. Okay, that's not so bad. Now here you'll see that in polar coordinates, this region has a beautiful description. Very simple. It almost feels like a rectangle when we say, well, r goes between this number and that number, theta goes between this number and that number. Because if we were in Cartesian coordinates, we said like x goes between 1 and 3 and y goes between 2 and 4. That would be a rectangle. So here in polar coordinates, it becomes a slightly different shape. Now, there's another part which builds right off of this and says, well, let's describe this using Cartesian coordinates. Well, there's a couple of ways you could do this. One thing is we could say, well, what are some suggestions?
One is less than or equals x squared plus y squared less than or equal to 4.
Okay. So someone has said, well, let's just take this relationship. Let's square everything. So 1 squared becomes 1 less than or equal to r squared less than or equal to 4. So this becomes 1 less than or equal to x squared plus y squared less than or equal to 4. That's okay. All right. How about that takes care of this part? How do we take care of that part? Okay, so we want to bound x or y. How can we do it? So we can say x is greater than or equal to 0. That guarantees that x greater than or equal to 0 says you're over here. And we don't need to say x is at most 4 because that will be implicit in here. Actually, x is at most 2. But, and y is greater than or equal to 0. So this could work. Now, suppose for a second we were going to do integration to find the area of this shape. Now, would we do integration? No. We would just say that just take a big circle minus a little circle. But let's just show how absurd this would be, just for fun. All right. So do you want to slice things up vertically or horizontally? Vertically. Okay. So if we were going to set up integrals to find this, if we're slicing vertically, which means we're taking little slices like this, you'll notice that something happens along the way. In particular, there's this transition that happens. So before 1 and between 1 and 2. What happens? Well, what happens is that you have different curves that change in terms of the bounding curve. So between 0 and 1, it's this small circle that lower bounds. Between 1 and 2, it's 0 that lower bounds. So if you were after the area, well, you'd have to do two integrals, 0 to 1 and 1 to 2. Now, let's talk about the first integral. Well, what's the top curve here? Circle radius 2. So that's x squared plus y squared equals 4, which means if we solve for y, you get y equals the square root of 4 minus x squared. So you'd have the square root of 4 minus x squared. That's the top. Subtract, what's the bottom? Circle radius 1. So what would that look like? Square root of 1 minus x squared. That's the first integral. Then we're going to add to that in the second integral from 1 to 2. It's the same top, square root of 4 minus x squared. And what's on the bottom? 0, because it's the axis. Now, if you look at this integral would be the frowny face emoji, because that does not look like a fun integral to do, because it's not a fun integral to do, unless you appeal to geometry. If you don't appeal to geometry, that takes you a lot of time. By the end of this week, we're going to come back and do a problem like this using a way of doing integration to knock it out, and it'll be fairly quick. Okay, so we're getting pretty comfortable. We can switch from polar into rectangular. Well, let's see if we can do the opposite. Let's see what would happen. So convert the following into polar coordinates. And let's see if we can see what happens. All right, so we have a bunch of problems here. How do we do it? Well, the basic thing to remember, it's actually incredibly simple. If you're going to convert from Cartesian into polar, the root formula to use, or rather the pair of formulas to use, are x equals r cosine theta, y equals r sine theta, and if you want to throw in a third bonus one, x squared plus y squared equals r squared. If you remember those facts, then these types of problems are very easy. They work themselves almost. Because what you can do is you say, if I have any set of equations, everywhere where I see either x, y, or x squared plus y squared, I just automatically put them in and life is good. All right. So let's start here. X minus 3 quantity squared plus y squared. Now we can either automatically plug in x and y, or we can rewrite and then plug in x and y. It doesn't matter. Which one do you want to do? Plug in x and y now, or wait a second and plug it in when we feel like it? Wait a second? Well, if we wait a second, what can we do?
Foil the same parentheses so we can get an x squared plus y squared.
Okay, someone has said we can FOIL this out, expand this out, and if we did that, you'll notice we'll get an x squared, and we have a y squared bonus. So x squared minus 6x plus 9 plus y squared equals 9. Now we can use the sophisticated fact that 9s on opposite sides cancel, which is cool. And if we combine, we have x squared plus y squared equals 6x. Well, now we're ready. X squared plus y squared becomes r squared, and x becomes r cosine theta. And the last thing we can do is we can divide by r. Now, I know that people are going to object, and some people are going to object to my objection, saying there's nothing wrong with dividing by r. There is a small technical thing you should worry about. What's our small technical thing? If r is 0. And my response to that is, don't worry about that. It works itself out. In all the problems where it means anything, it works itself out. So, and I know that's not a satisfying answer, and I'll point out why it's okay. So r equals 6 cosine theta is the answer. Now, why is it okay here? Well, is there any time when cosine of theta equals 0? Yeah, as an example, pi halves. So that includes r equals 0. So we didn't lose the fact that r equals 0 was a solution. So as a rule of thumb, don't worry about dividing by r. It's not worth stressing about. Okay, x cubed plus y cubed equals 9xy. Now, you're probably wondering what that looks like. I have no idea. I just made it up. It probably has some nice shape. I don't know. Maybe. But what can we do? Yeah, it's like, I don't see anything. Well, let's substitute in. So, r cosine theta cubed plus r sine theta cubed equals 9. R cosine theta, r sine theta. So, let's see. We have r cubed cosine cubed, r cubed sine cubed. Let's go ahead and pull out the r cubed. So you have r cubed times cosine cubed plus sine cubed. And here we have, we can pull the r's together, 9r squared cosine times sine. Now what can we do? Yeah, we could divide an r squared out. And by the way, most of the time that when we talk about polar coordinates, when we talk about polar curves, we really want to have that r equals something. R equals something, that's the ideal situation to be in. So if we divide out by an r squared, and then we divide through, we end up with r is equal to 9 cosine theta sine theta. Divide that by cosine cubed theta plus sine cubed theta. Now, what do we do with cosine cubed theta plus sine cubed theta? Good, that's the right answer. We don't do anything because there's no real simplification. And now we're done. Now we're done. Well, I mean, there are things you could do, but it's not going to help you much. Yeah, we'll just leave it at that. Okay, all right. X squared plus y squared equals x squared plus y squared plus x quantity squared. Wow. Huh, what could this be? Well, what do we do? Okay, some people have said use our substitutions. The x squared plus y squared will become r squared. And that's going to be equal to, well, x squared plus y squared is still r squared. Nothing's happened in the last 10 seconds. X, r cosine theta. And we're going to square that. Well, square root. Oh, that's a bold move. Okay, square root both sides. R equals r squared plus r cosine theta. Okay. Do we need absolute value? Ooh, that's an interesting question. Plus or minus r equals r squared plus r cosine theta. We'll come back to this in a second. Now what can we do? Let's divide everything by r. So plus or minus 1 equals r plus cosine theta. And we would write that as r equals plus or minus 1 minus cosine theta. So it seems to be that we really have one or two cases. Either r equals 1 minus cosine theta or minus 1 minus cosine theta. Okay, well that's curious. Now, what do you think? Suppose I ask the question. I have these two curves, r equals 1 minus cosine theta, r equals minus 1 minus cosine theta. And suppose I were to plot these two curves. What do you think they would look like in relationship to one another?
Here.
What?
I said opposites, right?
Opposites? What was that? It would be
The same with a different y-intercept.
the same with a different y-intercept. Ah, you're thinking Cartesian coordinates when you think y-intercept. I think these are actually the same curve. Now, I'm pretty sure people are going to disagree with me because they're saying in their minds, Steve, I know basic math, and I know that 1 is not negative 1. It's a true story, true story. Okay. But here's something else that's true. A flashback to something we said a little while ago. Remember something we said where we said, if I come up here to theta and I go out some distance r, if I compare that to going theta plus pi, but now I go not r but negative r, where do I end up? I'd end up at the same spot. So let's do the following. So let's come here, and I'm going to replace r by negative r, and I'm going to replace theta by theta plus pi. And I'll do it here to this second one. And let's just see what happens. If I replace r by negative r, that's negative r, equals minus 1 minus cosine theta plus pi. Now, what do we know about cosine of theta plus pi versus just normal cosine? So cosine is not pi periodic, it's 2 pi periodic. If I go pi, how does that relate? It's the exact opposite. It flips the sign. So this becomes minus r equals minus 1. Bring out minus minus makes this plus cosine theta. Now suppose I were to take this and multiply through by negative, what would we end up with? R equals 1 minus cosine theta, which is that one. So they would trace out, whoops, I ran off the bottom there. It would trace out the same set of points. So trace them out in a slightly different way, but it would still be the same set of points. Now you're probably wondering, okay, that's cool. What does this look like? Well, we'll talk more about that next week, but I can tell you that it looks a little bit like that. It's called a cardioid because if you turn it sideways, it looks like a bean. So that's what it looks like. All right, I've got 2 minutes left. I want to do one last thing because this is such a cool example. Archimedean spiral is the curve r equals theta. Now, this is a famous spiral because you can use it to trisect angles. So it looks something like that. It spirals out. So that the distance to the center depends on theta. Now, the thing is that this curve can be complicated to write. Suppose we wanted to write this in Cartesian coordinates. R equals theta. What could we do? Now, instead of humming and hawing, I'll just do something a little bit strange. Tangent of r would have to equal tangent of theta. Now, why do I do that? Well, I want to do something that helps me convert the theta. Tangent of theta does convert. Do you remember what tangent of theta becomes? Y over x. And tangent of r, well, that becomes tangent of r, and r is the square root of x squared plus y squared. So we get that y equals x tangent of the square root of x squared plus y squared. That's this curve. But if you had to ask which one is easier to work with, probably the r equals theta. So there are times when you want to work in polar. That's it for today. Come back next time and we'll do some more practice drawing. And have a good day.